Kia ora koutou, everyone. My name is Nick Braxton. I'm the Principal Sustainability Advisor on the City Rail Link project. Welcome to this webinar. There's 4 of us presenting today, so we'll be switching from one presenter to another. If you've got any questions, please submit them in the question box, and at the end of the presentation, the presentation itself is also available. I'd like to start off this presentation with a blessing or karakia. Homuru ki te rangi, homuru ki te papa, homuru ki te tangata, haumie, huie, haikea. Thanks, everyone. So the agenda for today is to have a quick project overview so everyone knows what the project's all about. The main subject of today is the carbon footprint of the project and what we've done to try and reduce that footprint. We'll talk about the embodied carbon of materials that we've used, the construction energy footprint. Then we'll look at some detail of the tunnels and what we've done to reduce the carbon footprint of the tunnels. We'll look at operational energy because our footprint includes 100 years of operation. And then we'll wrap up with questions at the end. So once again, please submit your questions as we go through in the question box, and we'll address those at the end. So first of all, a bit about the project. You can see on this slide here, this is Auckland CBD. Auckland's New Zealand's largest city. It's about 1.5 million people. It has a rail network. The current rail network is in blue, and you can see that the lines come in from the west, the south, and the east, and they currently all come into Waitemata Station, which is a dead-end station at the bottom of town. This project, which was actually first proposed in the 1920s, so we've finally got around to building it. It'll be running about 100 years after it was first thought of. This project is to remove that dead end at Waitemata Station. And all of this is overground rail, and it's an underground system right through the heart of the CBD and out to rejoin up to the Western Line out here. It'll involve 2 new underground stations and significant redevelopment of the overground station at Mongofo. The biggest impact it will have is that it basically doubles the capacity of the entire rail network. At the moment, all the trains have to come into Waitemata and then back out again. This will literally double the number of trains that we can run. So it has a big impact on the whole network and increases, it's equivalent to 16 lanes of motorway traffic going into the city without having all the disruption of what that would entail. So the physical build, so starting at the top right here, Waitemata Station, there's some early works packages that have tunnelled underneath that station, which is an existing heritage building, and using cut and cover tunnels up towards the first station, which is Te Waihoratu Station. That will be the network's busiest station when it's open. That's a 15-metre deep cut and cover station. From there, it's tunnel boring all the way up to Mongofo. There's the twin tunnels, 6.24 internal diameter tunnels. The first stop is at the Karanga Ahapi Station, which is a 33-metre deep mined station. And then continuing on to Mongofo Station, which is an above ground station. And then from there, there's a series of, there's mined and cut and cover tunnels at the connection of this area. And then from there, there's cut and cover tunnels rising up to grade to join into the existing network, which runs along here. So quite significant works to join all that up. So that's the physical construction of it. The project is currently, we're coming towards the end of the civil works. So that's mostly complete. The tunnels are all bored, and we're entering into a phase of architectural works and systems fit outs and so on. It's a roughly $3.4 billion project, and the vast majority of that is delivered by the Link Alliance, which is this group of companies. So City Rail Link, City Rail Link Limited, which is actually my employer, is the client organisation. The design partners are ACOM, WSP, and Tonkin and Taylor. And then the construction partners are Vinci, Solitaire and Downer. It's 50%, 50-50 split between the New Zealand government, and that will be that the rail assets will be owned by Kiwi Rail once it's completed, and Auckland Council, and the assets will be owned by Auckland Transport when it's completed. So that's a 50-50 split in terms of funding. All right, so the CRL carbon footprint, as I said before, our carbon footprint considers the construction and projected 100 years of operation. So we've got a mandate to try and reduce the carbon footprint for both of those phases, construction and operation. As you can see from this pie chart, about half of the total footprint is the embodied carbon of the material. So that's the carbon footprint related to the manufacture and transportation of the materials to actually build it. Another 11% of the footprint is the energy used on site to build it, that's construction energy. And then the remaining 40% is the electricity, mainly electricity used to operate the asset over its 100-year design life. And I should point out that operational energy excludes traction power. So this is the energy that's used to run the stations and rail systems, but not the actual traction power of the trains. So I'll now hand over to Neil to talk about that first big chunk, the 50%, that is the materials carbon footprint.
Thanks, Nick. Hi, everyone. So I'm Neil. I'm one of the sustainability advisor here on the City Rail Link project. And yeah, if we focus a bit more on materials, we can easily see that concrete is the main source of our emissions, followed by reinforcing steel, structural steel, and cement. To give you an idea, so carbon footprint of concrete is around 80,000 tons of CO2. This is roughly 185,000 meter cubes of concrete that's going to be poured, and it is the equivalent of like 40,000 trucks. So just to give you an idea of the project. So those calculations are mainly based on emission factors. We've displayed the main ones I display here on the chart. They come from the Infrastructure Sustainability Council, which is an independent rating tool based in Australia. The way to read this chart is if you take the structural steel, for example, on the left. So to manufacture 1 ton of structural steel, we emit 2.9 tons of CO2. So we talked about concrete. You can see here in blue in the center of the chart. What is interesting is that it's actually the cement, its cement content, and that drives the concrete emissions. One way to play with that is to reduce the amount of cement in the concrete design. So as you can see, the standard 40 MPa concrete's got a carbon footprint of 0.4 ton of CO2. But if you reduce its cement content, for example, replacing it with fly ash, it actually decreases to 0.3 tons of CO2. So we're going to talk a bit more in the slides afterwards. The other interesting fact here is if you take timber, you've got 2 different values depending on the approach taken. Where you've got the negative value, it means that it's considered as being as storing carbon and therefore removing some from the atmosphere. But if you take a whole of life approach, you also need to take into account the disposal of the timber once you've used it on site, and therefore it's got an impact and release carbon. Finally, you can see on the far right is the shipping. It's actually not that big of an impact compared to the manufacturing of product. So you can see here shipping 1 ton of materials for over 10,000 kilometers is actually, it's got quite a small footprint. So on a project of that scale, we've got different sustainability targets and KPIs. So one of them is to reduce our carbon footprint by 15%. So in order to do that, we need to establish a base case to have a point of comparison. What we've done on the project is we've taken the reference design, which was developed by the client. We've basically gone line by line, extracted the quantities. So like you can see here for this particular cabin beam, and then multiply those quantities with the relevant emission factors that we just saw in the previous slide. Regarding design, it's a bit more complex. So we first collaborated with the BEAM team. So BEAM stands for Building Information Modeling. So the team developed a 3D model of the stations and tunnels that needed to be built. And they've quantified, within this model, they've quantified all the concrete and steel that will need to be used for the construction. So again, we've extracted those volumes and quantities and used them to create the detailed design carbon footprint. So as you can see, we've been able to track month over month the progress of the design, and then feedback to the designers on the impact their choices had on the carbon footprint of the project. Finally, the last chart is we've used those base case and design footprints and to be able to compare, to monitor and track against our actual footprint once construction started. As you can see, the red line is our base case, the blue line is our detailed design, and the green line is our actual. You can see we actually tracking at 15% below our base case. And this is due to a few different initiatives that I'm going to talk in the next slide. So the one I've briefly mentioned is around concrete mix design. We expected an 18% reduction in our concrete footprint. This is mainly due to an average of 21% replacement of cement with fly ash. This might not seem a lot for if you are in another country, but here in New Zealand, the current replacement for the current average of a cement replacement is only 2%. So it's quite a big jump that we have on the project. The second one is around design optimization. As you can see on the bottom left corner, we've removed the central edit at one of our stations, which reduced the amount of tunneling required by 11%. And therefore reduce the amount of shotcrete, concrete, reinforcing steel that was needed. Changing in methodology, so we've changed from bottom up to a top down construction, and as you can see, it means we didn't need some of the temporary steel props that you can see in the pictures. The only drawbacks was that we had to increase the thickness of some of the walls and slabs, offsetting a little of the benefits of these initiatives. And finally, we changed for some of the works. We changed from piling to D-wall. D-wall being a bit more efficient way to build some of the elements, requiring lower volumes of concrete and steel. This was a brief overview of the materials. I'm now going to hand over back to Nick to talk about construction energy. Thank you very much.
Thanks, Neil. So as you saw from the original footprint, we've got that's 50%, Neil's talked about 50% of our footprint. Construction energy is actually the smallest part, or that's kind of the most visible. You've got all those big machines on site churning out lots of diesel fumes. In fact, it's only 11% of the footprint. So I'll just talk quickly through how we calculated that. So Neil mentioned that for the materials, we had a reference design which had quite a detailed list of all the materials expected to be used in our baseline. The reference design doesn't have that same kind of detailed information around what will be used to construct it. That's not the sort of level of detail you get in a reference design. So what we did in order to set a baseline that we could compare ourselves against is we worked out, based on our detailed design, we worked out, the constructors worked out, what machines they're going to use and how long they're going to use for and how much diesel they're going to use, et cetera, et cetera. And we obviously had a whole lot of initiatives that we implemented, that we were planning to implement to try and reduce the carbon footprint of all of that. So what we did is we looked at our footprint for our detailed design. We looked at that, we worked out what the initiatives, how much they was expected to save, and then use it to backcast back to a baseline that we can measure against. So a baseline is basically a detailed design without the initiatives that that we've added in. So it's a design that's using a business as usual technologies effectively, with no focus on reducing the carbon footprint. So for example, here we've got, we'll talk about it later as well, a lot of the original design had a lot of piling with, secant and contiguous piles, etc. We replaced quite a lot of that work with diaphragm walls. So we've worked out, okay, did that save us any emissions, on-site emissions for that? And we've put that into our savings. So I'll just talk through some of the details of where we've got their savings. We're expecting a 19% reduction in our construction emissions carbon footprint, and that really comes from 5 main areas. First of all, as I mentioned before, we've changed a lot of the piling methodology, changing from piles to D-walls, a lot of other changes to the piling approach, doing more detailed site investigations so we could work out, so we could absolutely optimize the piles we're using, changing from secant piles to contiguous piles in various areas, all sorts of different changes, even keeping an existing wall that we originally slated to be demolished, we found we could reuse that. So a whole lot of things there have created quite big savings in piling, which is a very big part of the construction footprint. Another thing we've done is, where possible, we've tried to use grid electricity. New Zealand has, the New Zealand grid is about 80 to 85% renewable energy, mainly from hydro, geothermal and wind. So anytime you switch from using a diesel powered machine to a grid connected machine, you get about an 80-85% saving in your carbon footprint. So that's the single biggest thing we can do. A good example of that is these multi-service vehicles, which used in the bored tunneling. They deliver the segments to the tunnel boring machine and people and other equipment. We used electric MSVs. We actually had 5 MSVs, 2 were diesel, 3 were electric. The electric ones, battery electric with regenerative braking. The advantage of our project is that it's all downhill, so that the MSVs are traveling downhill loaded and therefore recharging the battery, then go uphill empty. And they're relatively short tunnels, so that worked quite well, and about half of the segments and so on delivered by these electric MSVs. Another thing we did is really tried to optimize the plant to make them as efficient as possible. This picture on the right here, you can see this is a telescopic excavator at the Tiwai Horoshu station. The previous part of the project, they'd had excavators, several excavators. You found that spoil could be handled multiple times before it left site. Using a telescopic excavator meant we could just reach right down to the bottom, the 15 meters down, to reduce the number of times that spoil was handled and increase the efficiency of the excavation. And excavation is a really major part of the project. About 1.6 million tons of spoil have been excavated. Neil mentioned before things, design optimization, and Wataru is going to talk about it as well. Where we've removed things like excavation and obviously, removing a whole section of tunnel here reduces the amount of spoil you have to excavate, the amount of energy used on shotcreting, et cetera, et cetera, et cetera. So that really reduces the construction footprint as well. And then lastly, spoil haulage. Spoil haulage, we're working in the centre of the city. Most of the place we've tried to minimise how far we have to transport that spoil, but there's limited places you can put it in a city. So often it has to be transported a big distance, and actually nearly half of our construction footprint is actually just transporting spoil. So we really work with our subcontractors. We worked on putting in driver training schemes to increase the efficiency of the driving of the drivers, which has been quite worthwhile. I think both our main subcontractors have really found that valuable for the other parts of the business as well. And then we've focused on really trying to maximize load size. So, having scales to make sure that we're loading them to the exact right amount, not too much, obviously, for safety reasons, but maximizing the load size so we can reduce the number of trips. So that's had a big impact, well, a reasonable impact on our footprint. I'm now going to hand over to Wataru, who will talk about some of the work we've done on the mine tunnels in particular.
Yeah, thanks, Nick. So my name is Wataru. I'm the tunnel discipline lead on this project. So we're going to spend a bit of time looking at design optimization in the tunnel design space. So the sketch at the top is the reference design. It was provided by the council for the tenderers who were bidding for the detailed design and delivery of the job. And the figure at the bottom is the detailed design which we developed during the delivery phase. So the key thing to note is that we substantially reduced the blue section of the tunnel, which is the mined tunnel. The big advantage in doing that is mined tunnel is relatively carbon heavy because we need to use a lot of shotcrete as a temporary support, and we also need to come back and build a permanent lining with in-situ concrete. So what we did right at the start is to move the yellow cut and cover section to the left so that we can reduce mine tunnel and some of TBM tunnel. In the cut and cover tunnel, we have more space for construction plant to operate, so we have more efficiency in terms of construction energy footprint, and that way we were able to substantially reduce mine tunnel. There's also cost and I guess safety advantage on top of a carbon footprint. The other thing to note is on your left, we had a 127-meter long mined tunnel, which is a cavern for the rail bifurcation Y junction. So we optimized the geometry and the alignment, and we reduced the mined tunnel as well. So what it does is we reduced the mine tunnel, and we also increased TBM tunnel. So essentially, we are switching from diesel-powered plant, which is used for mine tunnel, and we are switching to TBM, which is powered by the grid. And the other thing to note is we invest a fixed amount of carbon footprint in the manufacture of TBM, and by making TBM tunnel longer, we are kind of spreading the initial investment over longer lengths as well. Next slide, please. Right, okay, so we also looked at geometric optimization of mined cavern, where we have a rail one junction. So the reference design was made up of a series of constant profile in step changes. So in the detailed design, we looked at kind of tapered geometry. So this involves slightly more complex construction methodology, and a special formwork, but our construction team had expertise in this area. So the net result was that we substantially reduced the volume of excavation and lining, concrete lining, and it also helps the ventilation, airflow, and all that. So therefore reduces the operational energy aspect as well. And we did use formwork, custom-made formwork, but we basically made formwork to work in such a way that it can be recycled for every single pour, so that we sort of minimize the waste in that space. Next slide, please. Right. So we look at volume optimization, but we also looked at alternative material, which give us a saving in the carbon footprint. So in New Zealand, traditionally we've been using steel fiber reinforced shotcrete for tunneling work. And so that was what was specified in the reference design. But in our case, we look at alternative material, which involves using polypropylene fiber reinforcement in the shotcrete. And this was done in overseas project, and our construction team had some experience using this material. So we did a little bit of testing before we introduced it to site. And again, so this resulted in carbon footprint reduction in terms of the embedded carbon. And because of the larger volume, it gave us quite a bit of saving as well. Okay, next. Right, so I'm going to hand over to Andrew Lester, who will tell us a bit more about operational energy.
Yes, morning everyone. My name's Andrew Lester. I'm a principal mechanical engineer here at WSP in Auckland, Tamaki Makaurau, and on this project I'm the mechanical fire and hydraulics lead. So my involvement with the sustainability team here has been to assess the operational energy of the stations. We build these things, it takes quite a lot of carbon to set them in place, but then we also have to run them, and our footprint takes into account 100 years worth of that. One thing to note, I suppose, is that often with operational energy, it does tend to be a fairly large chunk of the footprint over the life of the project. With these being fully electric stations, there's no gas, there's no combusted fuels on site. And with the New Zealand grid being as clean as it is, that means that we do tend to have a smaller footprint than we might otherwise for the operational energy part of the cycle. Nick, if you can go to the next slide, please, we'll step through some of those benefits. Yeah, so just looking at, again, looking at that 40% is made up of 40% carbon, not necessarily of energy. So that's the carbon footprint component related to the relatively clean New Zealand grid. What you can see on the left there is just an extract of the BIM model with all of the structure and architecture stripped away, kind of giving you a view of all of the services that run around inside these buildings and are hidden away behind the carbon and the steel, the concrete and the steel, I should say. In particular, you can see the big tunnel vent fans there in the kind of greenish yellow color. Those ones are a pretty big contributor to the operational energy, and we'll talk a little bit more about those in just a moment or so. Thanks, Nick. So similar to the construction energy, we had to do a backcast on our base case. The reference design was a very preliminary design, and it didn't really give us much to work from in terms of operational energy. Another point to note is that the minimum requirements that we're working to on this project incorporate quite a lot of energy saving initiatives. And so we were compelled to use some of those as part of the project, but which would not be part of business as usual. The other thing that did happen on this project was a switch from 6-car train sets to 9-car train sets as the design basis partway through. So here in Auckland, we run 3-car multiple units, 6-car multiple units currently, but in the future, we're looking to run 9-car multiple units. That's 9 train carriages in a row. In order to do that, the stations had to get bigger. They had to have different ventilation needs, different cooling needs. And so if we'd stuck with the pure reference design, it would not have been a very good representation of what we've ended up having to design for. In terms of our basis of decision-making along the way here, we've compared it to a business as usual design and construct contract. So that's sort of, I guess, harking back to the fact that where those energy saving initiatives were baked into the reference design, those aren't necessarily considered as part of the backcast. We've applied conservatism. We've tried generally with our operational energy to be a bit on the conservative side rather than being a little bit too keen with points that we might or might not be able to expect people to seriously achieve. And then we've also taken the view that we could reasonably expect some low cost or standard energy efficiency measures to be present. So an example of that would be the use of LED lighting. LED lighting's BAU as far as we're concerned. So we considered that as part of both the base case and our proposed case. You can go to the next slide, please, Nick. So just looking at some of those key operational energy benefits that we took advantage of within the tunnel ventilation, and those were those big fans that I was pointing out in the earlier earlier slide, we moved our operational energy strategy from a basic stepwise control, which is what was proposed at the beginning of the project, was more or less seasonally driven. So at the beginning of a particular season, we would turn them on to say 50% and run them, and then 100% and run them, to a temperature-based control. So we've implemented some temperature sensors down in the stations that will allow it to be operated more efficiently. It runs less of the time, and given they're such big fans, you know, they're sort of 350, 400 kilowatt fans, it takes quite a lot of power to run them, and it's good to reduce the amount that they operate. Mechanical systems, so within the mechanical engineering package, we've made use of EC fans. That's just a higher efficiency fan type than your regular AC fans. We've made use of higher efficiency chillers, so we're trying to use more or less the most efficient chillers that we can that fit our other needs, which is some of the packaging and the constraints around where they're allowed to sit within the stations. And then we've increased the operational temperatures in some rooms where it was acceptable to do so. So we've considered some of the rooms have equipment in them that is already ruggedized, and we can actually run those at a higher temperature, reducing their cooling burden. With the escalators, we've got high efficiency drives on those escalators, and we're using an improved sort of optimal control system from the escalator manufacturer that allows them to run lower speed more of the time and use less energy. Within the lighting package, as I mentioned, we have high efficiency fittings, LED fittings within our baseline and our proposed case. I still mention it because there's an important point around how you use your base case or between your base case and your proposed case, which I'll talk about when we come to the numbers in a minute. But I just wanted to mention it here that it is still important to take account of when you have those efficiencies in both your base case and your proposed case. The other thing we do have is full DALI control systems, which provide us with the ability to offer significant dimming to areas that are not used or not used frequently, as well as to those areas that are potentially overlit in the initial state because of the need to allow for the maintenance factor. We can benefit from having those lights turned down a bit more when they're not required to be at full brightness. Go to the next slide, please, Nick. Okay, so just looking at the detail on some of these operational energy results, we've got our backcast baseline on the left there, and then sort of stepping through each of those initiatives that I spoke about. In our case, actually, the energy reducing escalator controls were not a huge benefit, and part of the reason for that compared to some metro systems is that our escalators are not all that heavily loaded, especially in our early phases of our project. Our escalators are designed to handle the throughput of a fully busy station more or less 100 years from now with 9-car train sets running through it. So lots and lots of people coming through the stations means a few more escalators had to be built into the design, and we get a little bit less benefit out of them on day one than we otherwise would. DALI dimming was a big step for us. It has allowed us to take advantage of turning down quite a lot of those lights in quite a lot of areas, as well as reliably ensuring that they're turned off in areas that they're not required when they're not required. Temperature-based control of the tunnel ventilation fans, as I said, is a really big step change for us in terms of the amount of power that we were able to avoid using with those fans. So that was probably one of the single biggest changes we were able to make, and a relatively easy one to implement once we got over the initial resistance from the construction team on that one, but that was all good. Then the high efficiency mechanical plant, not any one of those big savings is a massive saving, but just the incremental savings of having quite a lot of small changes still added up to a fair amount. And so I would recommend to people to think about that as well, is that if you think, you know, each individual change is not that big of a change, that might be true, but if you can glom together quite a few of those small changes, it can add up to a reasonable saving. And then that takes us down to a proposed energy on the right-hand side, which is at the time of this estimate, about 22% lower than our initial backcast baseline. We can go to the next slide there, Nick. Okay, and I'll hand back to Nick now to carry on with the presentation.
Thanks, Andrew. So just to wrap up some of the things we've talked about today, I guess one of the things we've definitely learned is that the biggest opportunities are early in the design, which is probably no surprise, but the further along in the project you get, the reduction in the opportunities occurs. So you need to understand your footprint early, do some carbon analysis as soon as you can, work out where your big wins might be, and tackle those early in the project. I think it's also people probably right at the start of the project got more appetite for looking at things a bit more broadly, for at the end of the project when you're really looking at time and cost issues. So perhaps less time to think a bit outside of where you would otherwise be. We found the 3D modeling is really useful to understand that footprint. I think we had a reasonably manual process where we had, so monthly we'd get an extraction of all the quantity data from the BIM model. We'd then do our carbon footprint calculations and then share that information with the designers, which was great. I mean, we could, they knew where they were going on a monthly basis, but I think it could be a lot more automated. And ideally, you really want designers understanding instantly what the carbon footprint impacts of their decisions are, as well as having a bigger overview as well. So I think that's something that obviously can be done and should be done on future projects. On materials, there's a lot that can be done to reduce the concrete footprint. You know, we've done quite a bit in the New Zealand context where supplementary cementitious materials like fly ash and blast furnace slag. We only have one coal-fired power station in New Zealand. It doesn't run very often. So it's not a common thing to use, and we don't have access to blast furnace slag locally. So we've done quite a bit. We've pushed things quite a bit further forward. There's plenty more that can be done. The constructors need to be considering the impacts of how they use that concrete and just factor that into their construction planning because of the longer time to reach full strength, etc. The steel footprint, that's a really hard nut to crack. Basically, you need to design it out. There's not much you can do around steel footprint, really, in terms of the manufacturing process at this stage. Obviously, that's being worked on globally, but at the moment, it's really a matter of trying to minimize the amount of steel you're using. So thinking about how you balance your steel and concrete use, where you can do stuff on concrete, but you can't on steel. In New Zealand, switching to the grid is the biggest opportunity to reduce construction energy emissions. Obviously, it's hard to implement. We talked about the multi-service vehicles, the MSVs. They're obviously quite bespoke machines. We're pleased to be piloting those. There's some lessons learned going back to the manufacturer to carry on working on that and making those. We had some issues with them with recharging time and overheating batteries and so on, but they were really great. And they also reduced the ventilation requirements and so on of the tunnel, fire risks and so on. But in other large equipment, there's not many battery electric options at the moment. We've had some small excavators and things, but that's something that hopefully the industry will be providing more and more, the machinery. Lastly, surprisingly large savings can be made on operational lighting. Andrew mentioned that our baseline was LED lighting. We took that as being business as usual, so you kind of assume, well, that's all we can do on efficiency. But the daily lighting really did get us big savings in lighting. You know, harvesting daylighting or feature lighting, compensating for the age of the luminaires themselves, really made a big difference to the operational energy footprint, which is obviously a key part. In New Zealand, we're lucky that we have a pretty clean grid. In a lot of other places, the operational energy footprint would be a bigger proportion of your overall footprint. So those savings would be even greater. Okay, so that's the end of our formal presentation. So please do send us through your questions, and we will. I see there's already some through now, so we'll see if hopefully we can answer some of those.
Okay. Right. Thank you, Nick. So we have some time for questions and answers, but before we get underway, there's a copy of our presentation available in the handout box. And as Nick said, keep posting those questions in the question box. So the first question is, have you found any easy wins for future tunneling project to decarbonize? And if so, are these primarily on or off-site? Yeah, okay, I'll start off with this question. Yeah, so I think there are already widely accepted, I guess, practice in tunneling design space. So I didn't particularly mention this, but for the tunnel segmental lining, it's becoming increasingly common to use fiber reinforced concrete segment instead of steel bar reinforced concrete segment. I think that's becoming quite common, and I also touched on the polypropylene fiber reinforced shotcrete, and the fly ash. Use of fly ash is, I think, also kind of widely accepted practice. So there are easy, well, relatively common sort of initiative you can accept, and there are other initiative, design optimization is one of them. We probably have to look at it on case-by-case basis. And as Nick touched on early on, construction plant, we could look at using battery-powered plant as opposed to conventional diesel. So I think there's a number of things that we can look at, and hopefully our presentation give the audience some food for thought and ideas for future projects.
I saw, Watara, I saw there's a related question there. The question is, for the replacement of steel reinforcing with polypropylene reinforcing, was reduction from 35 kgs to 5 to 6 kgs a reduction in carbon? And if so, how was the reduction only 5%? So in terms of the carbon footprint, so that 5% reduction was reduction of the, not just the reinforcing, but the concrete as well. So we looked at the concrete with its reinforcing and worked out if we change out the steel fiber for the polypropylene, then we get that overall reduction of 5% for the whole thing. It also point out that the carbon footprint of polypropylene is actually higher per kg than steel reinforcing. So although yes, there's a significant reduction in weight, there is per kg that polypropylene has actually got a higher carbon footprint. So you don't get it's not a direct relationship between the reduction of weight in terms of reduction of footprint.
Yes. Yeah. Okay. Thanks, Nick. Okay. We have the next question. Has the carbon footprint of the air freight, sea freight to bring construction material in New Zealand being considered? Maybe this one's for Neil.
Yeah, we've considered it. So, for example, if we take fly ash, so we've got only one coal-fired power plant in New Zealand, which doesn't run all the time. So we have to import some of the fly ash, and we've done the comparison compared to importing fly ash compared to having sourcing cement in New Zealand, and it's still as I mentioned, its transport is quite small, so it doesn't offset the benefit of importing fly ash from India or China or elsewhere, because shipping has got quite a low footprint. So it's still much more efficient from a carbon perspective to import fly ash than to use cement locally sourced.
It would certainly be a different story if we were flying stuff in, then that's got a big carbon footprint, but most of the stuff we're using is obviously shipped.
Okay, thanks. All right, so the next question. In achieving the carbon reductions, what was the approximate impact on the overall project cost? How was selection of carbon reduction methods impacted by costs?
Good question. Generally, we find that costs and carbon reduction actually go in the same direction. So there's been some studies. There's a study that shows that for every 2% carbon reduction, you get a 1% reduction in cost, because if you're using fewer materials and so on, then you're reducing your cost as well as your carbon footprint. That's generally the case. There's definitely exceptions to that. We have tried to use, and where carbon reduction initiatives are expected to increase cost, we've used a bit of a rule of thumb of is it how much does it cost per tonne of carbon reduction? So at the moment in New Zealand, on the carbon market, carbon is about $70 a tonne. The New Zealand's Climate Change Commission estimates that the cost of carbon needs to be about $140 a tonne for the country to meet its 2030 emissions reductions targets. So we've used $140 a tonne of carbon as kind of the, if it's below $140 a tonne to do the saving, then that's something we should be seriously considering and trying to undertake. Whereas if it's more than that, then we consider that perhaps that's not the best value in terms of carbon reduction options.
So if I can sort of speak to an example of that, what Nick was just describing, we did look at escalator regenerative drives on the project, which are using the downhill escalators to help generate power for the uphill escalators. That added cost to the machine's first cost and also maintenance cost. We considered that against the energy savings that they would generate, and also against the carbon benefits, as Nick was saying, that then we priced that carbon into the equation. In the end, with the relatively low usage on our escalators compared to some international projects, and also the fact that our grid electricity is so clean to begin with, it didn't make sense, and so that initiative was not implemented. So that's an example going the other way, I suppose, of saying that would have been an example where it would have cost more to implement, and the whole of life cost consideration, including whole of life carbon consideration, meant that it didn't go ahead.
That's right, and maybe I can add to that, so that the project has a requirement to minimise whole of life cost. So that's and there's a formal process for looking at that. So that the incentive there is not to minimise on capex during construction and then have high OPEX. So there is a formal process to work that out. And I think, Andrew, the Dali, for instance, Dali lighting obviously has a higher upfront cost, so CapEx increases there. But the whole of life cost process shows that actually is a long-term whole of life cost benefit.
Yep.
So that process, and that we've integrated carbon, the cost of carbon at $140 a tonne into that whole of life cost analysis.
Yeah. Okay. So yeah, thank you, Nick and Andrew. Right. I think next question is kind of similar. So many of the sustainability initiative would have also resulted in cost reduction, construction cost reduction. Do you believe these changes would have been part of the detailed design process if the project wasn't an ISC project?
Yeah, it's a good question, and it's sometimes quite hard to know the counterfactual here. I would say that certainly some of the initiatives would have happened. So like we were talking about piling, you're going to try and, people are going to try and make it as efficient as possible for cost reasons. And I think in the end, any decision on one thing has got a whole lot of contributing factors. There's cost, there's time, there's, the availability of the machinery, there's all sorts of things that go into it. What we have done on the project is to make sure that sustainability is one of those aspects that goes into everything, and it's formally included in, so the change management process. We've got over 1,000 formal change management requests where something has been changed, a requirement or a design approach, and so all of those things go into there, including sustainability aspects. So we provide analysis on the carbon footprint impact of changes, for instance. And that is just one of the things that goes into it. So it is quite difficult to put your finger on, okay, what would have, if we had no sustainability requirements at all, what would have changed? There's some things that clearly have changed, and other things that, well, we might have done that anyway because it's going to save cost. So that it's a bit of a grey. There's some that's definitely done, some things that maybe we wouldn't have, and there's a kind of grey area in between.
Okay. Thank you. Right. Okay. Right. Okay. So the project would have, well, resulted in quite a substantial amount of carbon footprint in constructing it. And, how long till CRL becomes carbon neutral?
Yeah, that's a good question. Yeah, and one that's a good one to think about. Obviously, we do have a big upfront carbon footprint, and it wasn't actually in our scope to, obviously, we were brought on when the project had been decided. So I guess it's kind of a business case thing to consider. But it wasn't calculated in the business case in that kind of framework. So what I did to work this out was there's a consultancy that's worked out the carbon footprint of transport in Auckland, and then there's an interactive website where you can choose different things we can do to reduce the carbon footprint of the city's transport system. And helpfully, they have included building the City Rail Link as one of those things. So they've calculated that building the City Rail Link will reduce the carbon footprint of transport in Auckland by 28,000 tonnes of greenhouse gas emissions per year, and that's based on their modelling of change. It's quite a complicated thing to model, obviously. Change in behaviour of commuters, changes to where people build their homes, a whole range of factors. And so they've done that work for us. So we know our footprint. They worked out how much impact it'll have on an annual basis, and that means that in about 6.5 years, it should have paid back its initial carbon footprint. And so with an asset with a 100-year design life, that means that it's pretty decent. It's a good run from there. Another 90-something years of low carbon transport.
Okay, thank you, Nick. Right. Okay, so I guess how receptive was the client to incorporating the initiative? And do you have any suggestions on these client conversation? I guess obviously our client was actually a main driver, but for other clients who may not be so familiar, or they may not have same driver to sort of look at carbon footprint initiative, what tips or clue do you have to start these conversations?
I mean, something that I guess I would say, I mean, as you said, Wataru, that the requirements, the sustainability requirements on the project came from the client. And I think that will increasingly be the case as governments and so on have, climate change targets to address. But I think there's a cost argument that actually a lot of these things actually will save you cost. So that's probably a starting point. And I think there's also perhaps a social license question. Now, these projects have impacts on people when they're being constructed, and so I think if people know that it's doing a good thing in terms of reducing carbon footprint, not just when it's operational, but it's construction, that probably helps a bit with social license as well, making sure that it's a project that the public support, and I think our project has pretty broad support, although there has been some people significantly affected right next to the project. There is generally pretty good public support for it.
Okay.
Yeah, I think for the operational initiatives, if you're talking to a client that's got a longer term view, if it's an owner operator, if it's a governmental project, then a lot of those ones you should be able to demonstrate the value of these operational initiatives over the long term, because you will sometimes be putting in a bigger upfront capex cost. But you can use whole of life cost models to help with that, your NPV calcs and other things. That helps to support it when you're talking to someone who's got a longer view. Outside of that, I think, as Nick said, we do all have a social responsibility here to triple bottom line sustainability, and that is another vehicle that I think should be used when we're talking to our clients around it, is that at the end of the day, they're in business, they're trying to get things done for the community. There's not much point in doing that if we're destroying the future by doing it. So I don't know, that sounds, high level, but I think it is something we need to be calling back to our clients if they're just looking at CapEx costs right now.
Yep. Yeah. Okay.
Right. Well, I think we're sorry, Rotori.
Yeah. Just a few more questions. Right. Were solar panels considered to help with offsetting carbon?
Yeah,
Yeah,
we did.
Oh, you go, Nick.
Oh, so, no, you go, Andrew. No, you go.
Oh, no, I was just probably going to say the same thing, which is we did do some consideration of that early on in the project. The panels that we were able to source, or that we were able to reliably source, were coming out of China. Their carbon footprint in the manufacture phase was actually quite bad, and so our calculation of them in the New Zealand context, and with our space that we had available and the other factors that were in our project, meant that they were somewhat marginal. I think it would be fair to say, Nick, in terms of whether they were going to really make enough of a difference to justify their inclusion, because we do have that whole of life cost consideration as well as whole of life carbon. Is that a fair summary, would you say, Nick, of that early phase?
Yep.
Do you want to speak to later developments, or?
Yeah, well, we looked at it in some detail later on as we were, there was, lower embodied carbon panels became available. And in the New Zealand context, it still didn't quite add up in terms of carbon reduction, just because the electricity you're replacing is already pretty clean. So it came home to me when we were looking at, I think we were putting, I can't remember how many panels we were putting on, 170 panels or something we looked at putting on, there's only one station we could actually do it on, because our underground station, obviously, and looked at the carbon savings of that. Were equivalent to the carbon savings that my brother, who lives in Melbourne, was putting 15 panels on his home. And because in Melbourne you're replacing largely coal-fired electricity, he got a saving that's with 1/10 the number of panels that was similar to what we would get for 170 panels. So I think that kind of explained why it was quite marginal in terms of carbon cost. Payback time.
I think with the more recent panels that we found, with the lower embodied carbon panels that are coming to market, and with sufficient lead time on a new project, I would want to look at it again, because I think that those economics might add up differently as we move forward. But yeah, at the time that we could have baked them into the project, if you like, those early doors discussions, we just didn't have access to ones that were making a lot of sense.
Yeah, I think a lesson we definitely learned there as well is that it's quite hard to incorporate these things late in the piece, and actually it might be easier for the operator to install those panels after we hand the station over to them. So yes. Now I think we're running out of time, I think, so we should probably wrap things up. So apologies for the questions we haven't answered. We'll try and get back to you on those. So thank you all for tuning in. Just a reminder that the presentation is available for download, and we're all contactable on the email addresses that you see on your screen. So I'd like to finish off with a karakia. Homuru ki te rangi, homuru ki te papa, homuru ki te tangata, homie, tai kia.
Tai kia.